is Manmohan and Baljeet Singh from Himachal Pradesh University, Shimla. The title of their talk is Designing Dietary Fiber Psyllium-Based Hydrogels by Gamma Radiations for Use in Drug Delivery Applications. Yeah, he is already here. So the stage is yours. So you can proceed, Manmohan Singh. Yeah, sure.
Good afternoon to all. My name is Manmohan. I am a PhD student from Himachal Pradesh University, Shimla. My presentation is on designing dietary fiber psyllium-based hydrogel by gamma radiation for use in drug delivery applications. Controlled drug delivery technology represents one of the frontier area of science which involve multidisciplinary scientific approach contributing to human healthcare. Controlled drug delivery system can be used to achieve the sustained constant concentration of therapeutically active compound in the blood with minimum fluctuation along with the elimination of side effect. In general, the use of controlled dosage form may alter the pharmacokinetics and pharmacodynamics of the pharmacologically active moiety, decreases the toxicity, control the rate and the site of release of drug that act locally and the provide drug delivery system. The design of drug delivery system is equally important as the design of new drug molecule. A number of polymeric based devices have been proposed to achieve drug delivery system for efficient therapy. Among them, hydrogel specifically based on the polysaccharide have attracted considerable attention to act as smart candidate for controlled release of therapeutic agent to the specific site in GI tract. Polysaccharide based hydrogel. Polysaccharides are readily available, cheap, non-toxic, and are biodegradable. A large number of polysaccharide based hydrogel have been proposed for efficient drug delivery application. In present work, an attempt has been made to design the psyllium based polysaccharide for drug delivery system. Psyllium is a gel forming water soluble dietary fiber composed of arabinoids, xylose, raminoids, and galacturonic acid as structural unit. It has binding, emulsifying, suspending, stabilizing, and gelling ability. It is widely used for diarrhea, constipation, irritable bowel syndrome, and colon cancer, etc. Poly-2-methacryloxyethyl trimethyl ammonium chloride (METAC). Polymetac is a methacrylate type positively charged vinyl monomer. It is hydrophilic in nature and copolymer of metac with other hydrophilic monomer can form network structure in the hydrogel. Cefuroxime. Cefuroxime is a beta-lactamase stable cephalosporin antibiotic which is a broad spectrum in its action. It has been used for treatment of various GIT infection including respiratory tract infection, urinary tract infection, pharyngitis and skin infection. It works the same way as penicillin. They interfere with the peptidoglycan synthesis of the bacterial wall by inhibiting the final transpeptidone needed for the crosslink. In the experiment, the material used were psyllium polysaccharide, 2-methacryloxyethyl trimethylammonium chloride as a monomer, and model drug cefuroxime. The synthesis of polymer involves the grafting of vinylic monomer METAC to the psyllium backbone with high energy gamma radiation to form three-dimensional cross-link polymeric network, which is named as psyllium crosslink polymetac hydrogel. The result of psyllium crosslink polymetac hydrogels shows the same image of the psyllium show porous and smooth and homogeneous morphology of the psyllium. But after grafting vinylic monomer to the polysaccharide, the synthesized polymeric material show heterogeneity on the surface with formation of some pores. Pore enhances water absorption, which is a suitable feature for the hydrogel to be used in biomedical applications, specifically for drug delivery application. AFM tells about the topography of the polymeric material. In the AFM image, presence of some valley indicate the roughness on the surface. Rough surface enhances the mucoadhesion of the polymeric material to the site of drug delivery. Carbon 13 and FTI are images of polysaccharide and synthesized polymeric material shows characteristics peak for all the polymeric material or functional group moiety present in the materials. In TGA, thermal degradation of polymeric material as or polysaccharide both were analyzed. TGA explained thermal degradation with rise in temperature. For both polysaccharide or polymer, thermal degradation, excluding initial moisture loss, involved two-stage degradation. For both metrics, this degradation was corresponding to deep polarization, deep polymerization, decarboxylation, removal of quaternary nitrogen moiety from the polymeric material, as well as formation of cyclic aromatic compound during the thermal degradation. And in polymeric material, final decomposition temperature was higher in comparison to psyllium, which reflect the more thermal stability of the synthesized psyllium crosslink polymetallic polymer. Whereas DSA explained differential of heat flow through polymeric material in comparison to reference alumina. The psyllium crosslink polymeric material in DSC shows three exothermic peaks. XRD study of psyllium backbone as well as of that of polymer shows amorphous nature, and amorphous nature has increased after grafting of vinylic monomer METAG to the psyllium, which is conformed by full width of half maximuma and strain value. Mechanism of the reaction involves three steps. In first step, gamma radiation generate free radical on the psyllium backbone as well as on the METAC monomer backbone. In propagation step, these both psyllium radical as well as METAC radical combines to form psyllium grafted METAC macro radical and psyllium grafted METAC macro biradical. In termination step, psyllium grafted polymeric macrobiradical combines and get terminated to form final three-dimensional polymeric network named as psyllium crosslink polymeric polymeric network. These polymer was optimized by varying different reaction parameters. Swelling as a function of METAC. METAC content enhance the hydrophilicity of the hydrogel and cause the greater affinity for the water. This behavior can originate from the more quaternary nitrogen ion of METAC generated in the hydrogel network. These ions repel each other, and this repulsion tends to stretch polymer chain to extended state, which causes opening of polymer chain and overall increases the swelling of hydrogel. Swelling was also influenced by the radiation dose. Swelling ability decreased slightly as radiation dose increased. This was as a result of development of more cross-link and tighter structure between METAC and psyllium at high radiation dose, which hindered the mobility of polymeric molecule, reducing the diffusion of water within the hydrogel network. Swelling was also influenced by pH and temperature. Slightly more swelling of hydrogel was observed in pH 2.2 buffer as compared to the basic buffer, which may be due to opening of pore of ionic repulsion by the cation moiety of monomer and protonated group of acidic medium. Swelling enhanced with rise in temperature of the swelling medium due to increase in chain mobility. The non-Ficken diffusion mechanism was observed during the swelling of the hydrogel, and swelling show the synthesized material is temperature and pH responsive material. The release of sulfuroenzyme was also evaluated from the synthesized polymeric material. Drug release in all the medium occurs in sustained manner without any burst effect due to presence of various drug polymer supramolecular interaction in its three-dimensional network, which attribute to various binding site or functional group. Release of the drug was found higher in PBS and SWF medium. This was due to solubility of drug in basic medium. Ficken diffusion mechanism was observed, and release profile was best fitted to Higuchi kinetic model for the release, which indicated that mechanism of drug release from the blended hydrogel was diffusion controlled. The result of biomedical property shows that the synthesized polymeric material was non-thrombogenic, non-hemolytic, mucoadhesive, and antioxidant in nature. The result of present study confirmed that the change in feed of vinylic monomer METAC and radiation dose during the graft copolymerization reaction has influenced the cross-link density of the psyllium crosslink hydrogel, which has reflected in the swelling trend of the hydrogel. The porous three-dimensional network structure formed after the cross-linking were confirmed by SAM and AFM characterization of the polymeric material. Swelling studies showed that these hydrogel could absorb high volume of fluid in relation to their physical dimensions. The cross-linking density and hydrophilicity of the polymeric matrix and the pH of the medium showed effect on mechanical property and drug release profile of the gel. The result also showed that the release of drug occurred in controlled and sustained manner without any initial burst release and follow thickened diffusion mechanism. Biomedical analysis of hydrogel showed non-hemolytic, non-thrombogenic, antioxidant and mucoadhesive nature of the synthesized polymeric material. Overall result of swelling, drug release and biomedical property indicated that these polymeric hydrogel can act as potential material for drug delivery application. Thank you.
Okay, any questions from the audience? So I guess no. So I have one question.
Yes, ma'am.
So why you used psyllium?
Ma'am,
Uh,
psyllium. Yes.
yeah, yeah.
Ma'am, psyllium, ma'am.
Cellulose and starch, they can also be used. So why you specifically preferred this one?
Ma'am, psyllium has a more therapeutic value as it can use with do treatment of diarrhea, constipation, etc. And it is beneficial, more beneficial in comparison to starch and cellulose.
Okay. One more thing, for example, is this large scale production in industry is possible because you are using for the this method which you have told, because you are using gamma radiation, and
Yes,
gamma
ma'am.
radiation, see, they damage the tissue and harmful, they have harmful effects. So
Yes, ma'am.
large scale production, how it will be possible? So
Ma'am,
can
we
we?
can also synthesize it by chemical method. I do having another search where I synthesize same material with chemical or other physical cross-linker. This is autoclave.
Okay, okay, avoiding the use of gamma radiation because
Yes,
this
ma'am.
you cannot go for large scale
Yes,
production
yes,
with gamma radiations.
yes, yes. Actually, ma'am, we synthesize same material with the chemical method where we using cross-linker and an MBA and IPS monomer initiator.
Okay, okay, then that's all from my side also. So
Thank you.
shall we proceed further to the next speaker?
Prince ma'am, Dipali ma'am is here. I think we can
Okay,
call her.
okay, then we can call ma'am also. So the next speaker is Dr. Dipali Mahajan from GGM Science College, Jammu. The title of our talk is Greener Organic Synthesis. Madam, please.
A very good afternoon to all of you. Hope all are in good health. Should I share my screen?
Yeah, yeah, sure, ma'am. Please proceed.
Is my screen visible?
Yeah, ma'am, visible. But you can turn on to full screen mode. Yes, now it's okay.
So, today's topic is greener organic synthesis. As we all know, we are going towards greener chemistry. Green chemistry mainly focuses on reducing the impact of chemicals on human health and the environment. It emphasizes on designing of chemical products and methodologies, minimizing the hazardous substances, and maximizing the efficiency of a chemical process. The atom economy resulted in the usage of multi component reactions. These are convergent reactions in which three or more starting materials react to form a product where all or most of the atoms contribute to the newly formed product. The use of Lewis acids in organic synthesis is one of the most important fields in synthetic organic chemistry. The metal ions and their complexes are used in initiating and promoting varied type of organic reactions. Coupling metal ions with suitable adsorbent by virtue of their synergistic catalytic activity could prove efficacious in synthesis of the target compounds. Furthermore, the use of reagents impregnated on inorganic supports offer various advantages such as simple workup and product purification at the reaction completion, enhanced or reduced reactivity of the functional groups in the substrates, selectivity that may be different from that in the solution, and the manipulative simplicity. We all know the principles of green chemistry. So here the main emphasis is on alum, that is the greener catalysts. The salts of alkali metals react with equivalent quantity of sulfates of trivalent metals such as iron, aluminium, and chromium to form the soluble double salts referred as alums. The alums are crystalline in nature and are associated with 24 molecules of water of crystallization. Alum, also known as fitkari, was used for the treatment of water by Indians for hundreds of years. Being non-toxic and cheap, as an efficient, cheap, greener catalyst, it was used in organic synthesis, preferably used as Lewis acid in research institutions and industry to avoid the use of toxic organic reagents. The first reaction, the synthesis of benzodiazepines using alum under solvent-free conditions. Benzodiazepines are often used for short-term relief of severe disabling anxiety or insomnia. So here the cyclocondensation of 1,2-diamines with ketones in presence of non-toxic and cheap alum was done. A mixture of orthophenylene diamine, respective ketone, and pulverized alum was heated in round bottom flask at 80 degrees Celsius till the completion of the reaction as revealed by TLC, and the workup was being done. The spectral details: 2-methyl-2,4-diphenyl 2,3-dihydro 1H1,5-benzodiazepine. The 1H NMR spectrum showed 14 aromatic protons at delta 7.6 to 6.5, 2 singlets at delta 3.1 and delta 1.8 corresponding to CH2 and CH3. A broad singlet at delta 4.1 for 1 proton can be assigned to 1 NH. 13C and IR mass spectra were also done. So the next reaction is solventless one-pot synthesis of substituted benzimidazoles catalyzed by greener alum. A mixture of orthophenylene diamine and benzaldehyde pulverized alum were taken in RBF and heated at 88 degrees Celsius under solventless conditions till the completion of reaction as detected on TLC. So the compound was isolated in 96% yield as shown in the reaction here. The spectral details: IR spectra showed the peaks at 3056, 2960, 1597 corresponding to sp2 carbon, sp3 carbon, and C double bond N bonds. 1H NMR spectra revealed peaks at delta 7.80, 7.61, 7.39 to 7.32, 7.25 to 7.10. So all showing the aromatic protons and 2 proton singlet at 5.32, indicating the formation of 2-phenyl, 1-benzyl, 1H13-benzimidazole. Alum catalyzed solventless chemoselective synthesis of acylyls. The geminal diacetates or acylyls have been used as protecting groups for carbonyl compounds, the reason being the stability of acylyls in neutral, basic as well as acidic medium. When a mixture of benzaldehyde, freshly distilled acetic anhydride and pulverized alum was stirred at room temperature, an exothermic reaction took place, and after 30 minutes, according to TLC, the compound was being isolated. Alpha-alpha diacetoxytoluene benzylidene acetate. As revealed by its spectral data, delta 7.7 and 7.5 to 7.3 corresponding to the aromatic protons, and ARH, this 2.1 delta that corresponds to this CH3, the acetyl group. The IR and mass spectra were also done, 1760 centimeter carbonyl peak. Hybrid molecules are defined as chemical entities with 2 structural domains having different biological functions. The dual activity indicates that a hybrid molecule acts as two distinct pharmacophores. Both entities are not necessarily acting on the same biological target. Imines are biological active and are known to possess these biological properties. The three formyl chromone derivatives have been used as versatile building blocks for the synthesis of variety of heterocyclic systems. In addition to this, carboxylic acid hydrazides, they were also being used. So alum catalyzed solventless synthesis of imines of three formyl chromones. A mixture of 3,4-mylchromone, 2-aminobenzothiazole, and pulverized alum was heated at 80 degrees Celsius in solventless conditions for about 60 to 90 minutes till the product was being shown on the TLC. The spectral data shows the formation of 2,4-oxo 4H chromine 3-aryl methylene aminobenzothiazole. So these are the peaks: delta 8.81 proton singlet, 8.1 to 7.4, 7.71 proton singlet. So IR also showed the presence of 1680 and 1640 centimeter inverse. Solventless synthesis of hybrid molecules of 3,4-mile chromones using these carboxylic acid hydrazide. The same procedure was done, only the reactant was being changed. So spectral data shows the presence of 3,2-hydroxybenzoyl hydrozono methyl 4-oxo 4H chromine. This is the spectral detail showing the 1H 13C IR bands. So thank you for patient hearing.
So talk is open for questions. Any questions from audience? So I think no. So very nice presentation, Dipali ma'am. So I have one question. For example, you have prepared benzodiazepines and these benzimidazoles. So already there are so many methods available for the synthesis of these biologically important heterocycles. For example, benzodiazepines at room temperature, they can be synthesized from aluminosilicate catalysts. And at the same time, this benzimidazoles using boric acid at room temperature, we can synthesize. So how your method is better or is can be preferred over the earlier reported methods, because already we have so many
Actually,
methods available.
this is also a earlier reported method, not the new one. And
Okay.
every step towards greener chemistry, I think that is useful. This method has its advantage that we are using a very cheap catalyst, that is alum. Sorry, that is very easily available, no toxicity. So that is the advantage of this process. A very minimal workup is required. Almost a clean reaction is there, and the most important thing is that the greener catalyst, that is alum, that is being used here. That is the plus point.
Okay. Because boric acid also in
Yeah,
water at room
same
temperature.
same
Yeah.
the same reaction we have done with boric acid also.
Okay, okay, okay. So what was the difference in results? So this,
Almost the results are same. These reactions, they are multi-component reactions. They move easily. Single step is there. There are no side products. So whenever we have the reactions with no side products, that is the biggest advantage, where the workup is less. So that is the plus point. Boric acid also goes in the same way as alum.
okay. Okay, then thank you, ma'am. It's
Thank
indeed
you
a
so much.
privilege to be to chair a session where madam is presenting, because I was one of the students during MSc Dipali ma'am, she has taught us during MSc. So
Thank you
now
so
we'll
much,
proceed
Princy.
further. Yeah, ma'am. Thank you, ma'am. So next speaker is Himani Sen, Department of Chemistry, Himachal Pradesh University. So the title is Synthesis of Acacia Gum-based Hydrogels for use as controlled and sustained drug delivery systems. So
Ma'am, she's
present.
not here. She's not here, I
Okay,
guess.
okay. That is what I was going to ask. Presenter is here or not? Next is Sunitha, assistant, I think research scholar, Department of Chemistry, Tamil Nadu, narrow coil Tamil Nadu College. So synthesis, characterization, and antimicrobial activity of some novel azoamine compounds. So I think she is here.
Sunita ma'am, can you hear us?
I guess I have seen she is here. Right now, I don't know.
Sunita ma'am,
Yeah, I think Sunitha Christopher. Yeah.
ma'am, you are not audible. Please put your mic on. You're not audible.
Yeah, yeah, she is actually on mute mode. So, Sunita, madam, can you hear us? So, I think Gurpreet will proceed further. What do you say?
Okay, ma'am. We have Ambika ma'am and Upasana ma'am. Ambika ma'am is not here. I guess Upasana ma'am is in the meeting.
Okay, then whosoever will
Ma'am,
come
I'm there.
forward.
Ambika is there.
Ambika ma'am, you are
Yeah,
here.
yeah. Okay,
Yeah, I'm there.
Ambika madam is also here. So, next speaker is Dr. Ambika, Assistant Professor, Government Degree College, Kathua. The title is Reductive Amination of Aldehydes, a route for the synthesis of secondary amines. So, madam, you can proceed.
Okay. Good afternoon, all. I'm Ambika and I'm presenting on behalf of myself and Dr. Upasana Andotra. We both are assistant professors in Government Degree College, Kathua. And my topic is reductive amination of aldehydes, a route for the synthesis of secondary amines. So significance of amines is immense. A lot is known in literature about the significance of amines. Amines and their derivatives, they are very important functional groups in a variety of natural products. Drugs based on amine moieties abound the pharmaceutical industry. And amines and their derivatives, they act as precursors to a variety of biologically active compounds like pharmaceuticals and agrochemicals. So amines are moieties of immense significance. Three main routes available for the synthesis of secondary amines are: first is the direct alkylation. In this method, primary amine is treated with an alkylating agent and we get a secondary amine. No doubt this route appears to be very simple, but this is a very deceptive route because this leads to over alkylation of this nitrogen, leading to the formation of concomitant formation of tertiary amine also and quaternary ammonium salts also. So this is not a good route for the preparation of secondary amines. Then the second route available is by the use of protecting groups. In this method, we first reduce the nucleophilicity of this NH2 group by protecting it using an appropriate protecting group, and then alkylation is carried out. Then when alkylation on this nitrogen happens, then we remove this protecting group by a suitable deprotection method, and we get the desired secondary amine. Now, as it appears here, this is a long method. It involves two additional steps. One is protection and the other is deprotection. Moreover, while performing deprotection, sometimes methods are very harsh for deprotection, and during the course of deprotection, our desired secondary amine that also gets damaged. Now, the third route is by the reductive amination of aldehydes and ketones. So for that, amine is primary amine is treated with an appropriate desired aldehyde or ketone, leading to the formation of imine, and then this imine is reduced. This double bond, C double bond N, we reduce this and we get the desired secondary amine. Now, this is a very preferred method for the preparation of secondary amines because there is no concomitant formation of tertiary amines or quaternary ammonium salts in this route, and moreover, protection deprotection procedure is also not involved in it. So uh, we try to develop a good method for the reductive amination of aldehydes and ketones to synthesize secondary amines. For this, uh, we use this thing. This is basically a tandem reaction. First of all, we treated desired aldehyde with a desired primary amine to get the imine. Now, this amine was then subjected to reduction by in situ generated benzimidazolene, and that in situ generation of benzimidazolene was achieved by adding by adding aldehyde and orthophenylene diamine to the reaction mixture. Once the formation of imine was achieved as indicated by TLC, then we added further aldehyde and orthophenylene diamine. This led to the in situ generation of benzimidazolene, this moiety, and then this benzimidazolene transferred its hydrogen to the imine, leading to the formation of the secondary amine and benzimidazole as a byproduct. So, initially, when we carried out this reaction, we treated equimolar mixture of aldehyde with primary amine, and we got the imine as indicated by TLC and established by other methods. Then this imine was then subjected to reductive amination with in situ generated benzimidazolene by adding equimolar mixture of again aldehyde and orthophenylene diamine. And then we got these two products. But the main problem was that this yield of this reaction was very less. It was just 76%. So in order to improve the yield, we carried out the same reaction under different reaction conditions. First change that we made was by using molecular sieves. Then we carried out this reaction under nitrogen atmosphere, and under nitrogen atmosphere, yield of this reaction got improved to almost 76%. Then further we made further changes in the reaction procedure. We carried out this reaction at room temperature in ethanol under nitrogen atmosphere using 5A molecular sieves. And in that case, at room temperature, the yield was very good. It was almost 94%. And then we established this methodology, and we subjected different aldehydes and amines to these reaction conditions to obtain desired secondary amines. As far as the procedure is concerned, on the completion of the reaction, as was indicated by TLC, we added almost 25 ml ethyl acetate to the reaction mixture, and then we filtered it. On filtration, we got this benzimidazole as a residue, because this is a solid at room temperature. Its melting point is above 200 degrees Celsius. So we got this benzimidazole as residue, and this as residue, and the filtrate we got. The filtrate was subjected, then was it was proper workup was done with the filtrate. It was washed with water 2 to 3 times. Then it was filtrate was washed with brine, and finally it was dried over in hydrous sodium sulfate. And then it was reduced, it was concentrated under reduced pressure to get the crude product. The crude product was then separated into different products by using column chromatography. And then the different products obtained were subjected to different spectroscopic studies. And those studies established the formation of this desired amine. In good yield, we got this thing. So in this slide, I have shown how we optimized the reaction conditions. Initially, we were getting just 76% of the yield. Then we carried out this reaction in ethanol at room temperature under nitrogen atmosphere and in presence of IV molecular sieves, and the yield got improved to 92%. This benzimidazole was obtained in 92% again, because this is the moiety which leads to this reduction, as was indicated in the previous slides. Now this slide, this shows different amines and aldehydes that were subjected to this reaction to get the desired secondary amines. This 1 minute. Then now here we have represented a multi-component reaction. Since the reaction that I discussed earlier, there we were following two steps. First, there was the formation of the amine, and then it was subjected to in situ reduction by the generation of benzimidazole. Here we have carried out a multi-component reaction, because multi-component reactions are very easy to handle. So here we made a change. We carried out this reaction in a single step as a multi-component reaction. We used two equivalents of the aldehyde, one equivalent of the primary amine, and one equivalent of the orthophenylene diamine. So one equivalent of this aldehyde, it got involved with this amine, leading to the formation of amine, and the other equivalent of this aldehyde, 1 minute, of this aldehyde, it reacted with this orthophenylene diamine to generate benzimidazole, which transferred its hydrogen to the amine, leading to the formation of this amine and this benzimidazole. So we carried out the multi-component reaction also, and this made no effect on the yield of the desired secondary amine. There was no effect. Hardly 1 to 2% change in the yield was observed, and that may be due to the manual reasons. So we carried out the multi-component reaction also with this methodology as a multi-component reaction also. So advantages of our methodology are that it doesn't involve the use of any acid as catalyst. No activation of C double bond N is required for this reduction, and moreover the byproduct benzimidazole, it can be separated by simple filtration. Now these are the spectral details of few compounds, secondary amines that we prepared by this method. So this secondary amine, it was obtained as a yellow thick oil, and its 1HNMR was recorded, which showed 9 hydrogens as singlet at delta value 3.84. These 3 from this methyl, 3 from this, and 3 from this. Then we got a singlet for 2 protons at 4.26 delta value, these 2 protons, and then we got a multiplet for 5 hydrogens in the aromatic range between 6.61 to 6.76. And another multiplet for 2 protons at in the range 7.16 to 7.25. Here I have shown the C13 NMR data also of this compound. And then this representative compound, this was obtained as a transparent thick oil, and its 1HNMR, it again showed a singlet for 4 protons, these 4, 2 these and 2 these, at 4.31, and then it showed multiplets in the aromatic region. For 6, it showed a multiplet in the region 6.61 to 6.73, and for the 8, it showed a multiplet in the region 7.14 to 7.38. So here is a C13 NMR detail also for this compound. That's all from my presentation. Thank you.
Yes, one question from Nazar Hussain.
Yes.
I have a question. I'm very curious to know that why you have used this benzimidazole as a hydride source, because in initial step you are getting aminium ion, and then it's really simple to reduce it with sodium borohydride or any other hydride source, but you are again coupling with the diamine with aldehyde, and then you are transferring the hydrogen to get this secondary amine.
So one thing was to get a method which resembled some biological process. So in order to carry out a biomimetic type of organic reduction, we use this benzimidazole, and moreover, the benzimidazole generated in this reaction as a byproduct, it is of immense biological significance also. So we carried out this method in the search of biomimetic reducing agent.
So you mean this benzimidazole is a biomimetic reducing agent? But
It's not exactly a biomimetic reducing agent, sir, but it behaves like that. It behaves like just like that a Hans ester sort of something.
so in conclusion, you are just getting a waste with your reaction because your actual product is the secondary amine, not the
No,
benzimidazole.
no, sir. In this
Why you
reaction,
are
I'm
wasting
getting
benzimidazole?
different types of different. I'm getting a series of benzimidazoles also, and benzimidazoles are also having immense biological significance. Their significance is immense in the literature available.
Okay, thank you.
Okay, Ambika, madam, I have one question. So, what about the individual yields of amine and benzimidazoles? So, how much percentage of amine and benzimidazoles you got?
Ma'am, it was almost parallel because 1 minute, ma'am.
Means 50-50 you are getting,
No,
or
no, no.
like,
It was not
okay.
50-50. 1 minute, I'll show you. Ma'am, if it was almost in 76% yield, then benzimidazole was also in that range.
Then out of 100%, how much percentage of amine you are getting and how much benzimidazole? Because you already told simple filtration, you will separate benzimidazole and then
Yes.
amine. Yeah, just I want to know.
Ma'am, actually, with respect to this amine, primary amine, I got this secondary amine in the yield 92%,
Okay.
and this benzimidazole in parallel 92%. In some cases, it was bit different, like it was 92 or it was 91 or 93, 94, like this, but their yields were parallel. Because this is the moiety, benzimidazolene is the moiety which transfers its hydrogen quantitatively to the imine.
Yeah, yeah.
So their yield has to be.
So this whole process is one part synthesis, right?
Finally, it was one pot synthesis.
Okay, that's all from my side. Thank you, Ambika madam. So we'll proceed to the next speaker. So next speaker is Professor Jagdish Kumar and Professor Rashi Gupta.
This year will be presenting today. He will be presenting tomorrow.
Okay, so now I think all done. So anyone who has
Ma'am,
joined,
Himani.
yeah, yeah,
Himani,
sure.
Himani, ma'am, you are here? Okay.
Yes, Himani. Okay, so the next speaker is Himani Sen,
Yes, ma'am.
Department of Chemistry, Himachal Pradesh University. So the title of her talk is Synthesis of Acacia Gum-Based Hydrogels for Use as Controlled and Sustained Drug Delivery Systems. So Himani, you can proceed.
Okay, ma'am. Good afternoon to all of you. I am Himani Sen. I am AMPHO student from Himachal Pradesh University, Shimla. My topic is synthesis of acacia gum-based hydrogels for use as controlled and sustained drug delivery system. First is introduction. An optimal drug delivery system ensures that the active drug is available at the site of action in an appropriate concentration for sufficient long time. The drug concentration at the site of action should be above the minimal effective concentration and below the minimal toxic concentration. Controlled drug delivery system decreases the toxicity and occurrence of adverse drug reactions by controlling the level of drug in the blood at the target sites. In present work, an attempt has been made for synthesis of acacia gum-based hydrogels for use as controlled and sustained drug delivery system. Then hydrogels. Hydrogels are hydrophilic, three-dimensional networks of polymer chains. In order to maintain the three-dimensional structure, the hydrophilic polymer chains are cross-linked either by covalent bonds or non-covalently by electrostatic or van der Waals interaction. Hydrophilic groups and interstitial spaces exist within the network to retain water molecules. This is the quality brings about the specific benefits of hydrogels in drug delivery. They function as a controlled drug delivery devices. They are capable of releasing drugs at specific target site. Material used. First is acacia, then polyacrylamide, 2-acrylamido, 2-methylpropane sulfonic acid, that is AMSA, N-methylene bisacrylamide, that is NNBA, then levofloxacin. First, acacia gum. Acacia gum is mainly composed of four chemical constituents, namely arabinose, galactose, rhamnose, and glucuronic acid. It has wide applications as a stabilizer for emulsions, a binder, and a coating for tablets, and as an ingredient in cough drops and syrup. It is also used in food and cosmetic industry. Then polyacrylamide. Polyacrylamide is a cross-linked product of acrylamide. Polyacrylamide is non-toxic, biocompatible, highly hydrophilic, forming a gel when hydrated. It has been used as material for various biomedical applications, including drug delivery applications. 2-acrylamido 2-methylpropane sulfonic acid, that is called AMSA. It is a reactive hydrophilic sulfonic acid acrylic monomer used to alter the chemical properties of wide variety of anionic polymers. Then NNBA, that is called N-methylene bisacrylamide. It is a cross-linking agent used for the formation of polymer. Levofloxacin. Levofloxacin is a fluoroquinolone antibiotic that fights bacteria in the body. Levofloxacin is used to treat a number of diseases such as pneumonia, urinary tract infection, chronic prostatitis, and gastroenteritis, etc. Common side effects include diarrhea, nausea, headache, and constipation. Synthesis of acacia gum based hydrogel. Synthesis of polymer involves vinylic monomer, that is acrylamide and AMSA, in the hydration for 3 hours at 65-degree temperature to form cross-linked hydrogel. Mechanism. The mechanism is carried out by graft copolymerization. The graft copolymerization take 3 steps. First step is initiation step. In this step, free radical on acacia backbone, and the second step is propagation. In this step, both radical, that is acacia backbone and vinylic monomer, to form a homoradical, and after it form the macroradical. Third step is termination. In this step, the product is made acacia cross-linking polyamsa co-linking acrylamide network. As the swelling as a function of acrylamide, swelling of the hydrogel firstly increase, then decrease as the concentration of monomer increase during the formation of the hydrogels. Swelling of hydrogel prepared with different acrylamide content occur through mechanism which is approaching towards non-frequent diffusion mechanism. Swelling as a function of 2-acrylamido 2-methylpropane sulfonic acid, that is AMSA. Swelling of hydrogel was influenced as the content of AMSA was varied and swelling followed non-frequent diffusion mechanism. Swelling as a function of NNBA. Swelling of hydrogel first increases, then decreases with increase in NNBA. Swelling of the hydrogel prepared with different NNBA content occur through mechanism which is approaching towards non-frequent diffusion mechanism. Drug release studies. Release of levofloxacin occurred in slow sustained manner. Maximum release was found in pH 7.4 buffer. Drug release occurred through non-frequent diffusion mechanism. Conclusion. Swelling of the hydrogel firstly increases, then decreases as the concentration of monomer increase during the formation of the hydrogels. Drug release of hydrogels occurred in controlled manner. Drug release was found higher in pH 7.4 buffer as compared to pH 2.2 buffer. Overall, results indicated that these polymeric hydrogens can act as a potential material for colon drug delivery application. Thank you.
So now open for questions.
Yes, ma'am.
So any questions from audience? Okay, I guess no. So I have one question.
Yes,
Himani,
ma'am.
you are using acacia gum.
Yes, ma'am.
So as far as I know, acacia gum has adverse effects on our body, na? For example, nausea or something bloating it can cause.
Yes, ma'am.
So yeah. So so is it right to use this? It will have adverse effects later on also, for example, when we'll use it in drug delivery systems. Of Sunita madam is synthesis, characterization and antimicrobial activity of some novel azoamine compounds. So I request madam to please proceed.
Can you see my screen,
Yes,
ma'am?
yes, yes,
Okay.
it's visible. You can proceed.
I'm Sunida, research scholar from Tamil Nadu. My topic is synthesis, characterization, and antimicrobial activity of some novel azoamine compounds. Introduction. Azo compounds are considered as class of organic colorants which consist of at least a conjugated chromophore azo group in association with one or more aromatic or heterocyclic system. Sulfonamide antibiotics are utilized as veterinary drugs to treat infections in domesticated animals group. Furthermore, sulfonamides are very helpful drug compounds since they show a decent scope of organic exercises like anti-cancer, anti-inflammatory, and antiviral activity. Experimental synthesis of 2-amino-5-aryl 1,3,4-thiodiazole. Step 1. Synthesis of thiosemicarbazone. Aromatic aldehyde was dissolved in warm alcohol and thiosemicarbazide was dissolved in warm water. Both were mixed slowly with continuous stirring. The product separated immediately on cooling. It was filtered with suction, dried and recrystallized from ethanol to yield thiosemicarbazone. Step 2. Synthesis of 2-amino-5-aryl 1,3,4-thiodiazole. Compound 3 was suspended in 300 ml of warm water. To this add ferric chloride in 300 ml of water quantitatively, slowly with constant stirring. The curtains were heated at 80 to 90 degrees Celsius for 45 minutes. Solution was filtered hot and then citric acid and sodium citrate were added. The resulting mixture was divided into 4 parts and each part is neutralized separately with the aqueous solution ammonia. The recovered thiodiazole was separated out, filtered with the suction, dried and recrystallized. Then general method for the synthesis of benzylidine imine. 2-amino-5-aryl 1,3,4-thiodiazole compounds was dissolved in 30 ml of glacial acid and diluted to 50 ml of distilled water. To this equimolar quantity of aromatic aldehyde in 20 to 30 ml of ethanol was added and reflused for 6 hours. The reaction mixture was allowed to stand for cool. After cooling, the resulting reaction mass was poured into crushed ice and left overnight. The solid benzylidine imine were separated out, filtered, washed thoroughly with petroleum ether, dried and recrystallized from hot ethanol. Then general method for the synthesis of azodine. The benzylidine imine were dissolved in an ethanolic solution of sodium acetate with constant stirring. Sodium nitrate was dissolved in water and added to a well-cooled solution of sulfonyl amide initially dissolved in 3 normal HCl. The content were left at room temperature for 2 hours. The compound was precipitated and then washed with water. This is the synthesis of azo dye. Result and discussion. Table 1. Physical data of azo dyes compound 7, 8 to 10. Here R dash 3 hydroxy 4 methoxy benzaldehyde. Then compound 9 for chlorobenzaldehyde, compound 10 for nitrobenzaldehyde. Both compounds taken R2 as amide. Then melting point of compound 8 178 to 180 degrees Celsius, compound 9 176 to 178 degrees Celsius, compound 10 156 to 158 degrees Celsius, yield above 80% in all compounds. Molecular formula compound 8 C22H19 N6O4S2, then compound 9 C21 H15 N6O2 S2Cl, compound 10 C21 H15 N7O4 S2. Then FTIR data of azo dyes. The characteristic bands of IR spectrum of compound 7, 8 and 9 showed 1649 centimeter for the medium stretching of C double bond N group. Compound 10 showed 1648 centimeter. The azo compound N double bond N group at 1540 centimeter for compound 8 and 9 and 1528 centimeter for compound 10. The methoxy group is shown by 2764 centimeter and OH group is shown by 3735 centimeter for compound 8. Also the NH band at 3207 and 3206 and 3241 centimeter for compound 8, 9 and 10. The bands settled 763 for compound 9 CCl and 1346 for compound 10 CNO2. All the other bands in the spectra represents other functionalities of the synthesized azo dyes. This is the spectrum of compound 8 to 10. This is the proton NMR spectrum. The proton NMR spectrum of compound 8 showed a singlet at 3.835 ppm for methoxy proton. Then the bands 7.328 to 8.437 for aromatic protons. A singlet at 5.093 ppm for NH2 proton and 10.169 for OH proton. Compounds 9 and 10 also proved the protons. Then C13 NMR spectra. The C13 NMR spectra of compound 8 to 10 showed C double bond in carbon located in an region 156.59 and 156.49 and 148.08 are the aromatic carbon located in the region 122.68 to 132.54 ppm. All the other bands in the spectra represent other functionalities of the synthesized azo dyes. Antibacterial activity. Among the synthesized compounds, compound 8 to 10 showed good activity with the zone of inhibition 11 mm, 12 mm and 16 mm respectively against the bacteria E. coli. Compounds 9 and 10 were active against Bacillus tuberculus, while 10 showed good activity with Staphylococcus aureus. Compounds 10 showed moderately activity against Epsilon pneumonia as compared to standard drug streptomycin. The remaining compounds of the series possessed no antibacterial activity. Antifungal activity. The antifungal activity of the compound 10 was very active with the zone of inhibition 16 millimeter against Aspergillus flavus and a maximum zone of inhibition 60 mm against the Aspergillus niger. The compound 8 and 9 recorded with the zone of 8 millimeter and 9 millimeter against Aspergillus niger. The compound 10 showed good activity recorded with the zone of inhibition 11 millimeter against Rhizophus stolonifer, whereas the remaining compound 8-9 showed no activity against Rhizophus stolonifer. Conclusion: 2,5-phenyl-1,3,4 thiodiazole, 2-imino-substituted benzene, diacinate benzene, sulfonamide, 8 to 10 derivatives were synthesized and characterized. The constitution of these compounds assigned on the basis of IR, proton, and C13 NMR spectra were found to be in correlation with the desired structure. The antibacterial activity screening revealed that the compound 10 nitrosubstituted azoimine dye has more activity as compared to the standard drug streptomycin. In fact, the compound 10 exhibited antibacterial activity of equally greater than the standard drug. The antifungal activity show that the compound 10 nitro-substituted azoimine has good activity as compared to the standard drug fluconazole. Thank you.
So, any questions?
Yes, ma'am.
Any questions from audience? So, I think no questions from audience. So, Sunita, this work is already published.
Thank you, ma'am.
No, you have already published this work or in process?
Published, ma'am.
Okay. So, for example, you have done antimicrobial activities of these
Yes, ma'am.
compounds.
Yes.
These compounds, they are they show very good anti-diabetic activity also. So I think you can proceed with this activity also, biologically activity in
Also
future.
done, ma'am, antioxidant and anti-cancer also.
Okay. So what about the results?
Good, ma'am. Well,
Okay, because yeah. So that's what I was saying. You can proceed with these studies also. So then you can have good publications also.
Thank
So
you.
that's all from my side. So I guess she's the last speaker, Gurpreet.
Yes, ma'am. Yes, ma'am.
Okay. Then I think now I will wrap up this session. So I once again thank all the organizing committee members, principal of the college, for giving me this opportunity, and thanks Gurpreet also. So thank you all.